In the previous video, we had functions in which you knew intrinsically or directly how they're related to their independent variable x. But as we'll see in implicit differentiation and chain rule, that oftentimes we have a function that we don't know explicitly. We just know that it implicitly relates on some variable. So in these next two examples, we'll talk about how to work with that. So let's say that u and v are functions of x. So u and v are functions of x. So that's be true for the next two examples. And y is equal to, let's say, 3 u squared plus 8v cubed. And we want to know what is dy dx equal to. Now we're at some point going to get stuck because we don't know anything about u or v implicitly or explicitly, but we can still work out what the derivative of y with respect to x is, even though there's no x's anywhere. So first off, and this is really where being comfortable with differentials is very helpful, because the differentials actually, again, look at our rules, don't care anything about x. It's just how does a differential operator work with functions. So we first take the differential, so dy is equal to the differential of 3u squared plus 8v cubed. And by this point, I'm hoping that you recognize that this differential will distribute across addition. And well, let's just take baby steps. So I was going to skip a bunch of steps, but let's just go through. This is the differential of 3u squared plus the differential of 8v cubed. And now the differential we know will slide right past the constant, and we've got a power rule, so this exponent comes down and becomes my coefficient and reduces by 1. Same here, the differential slides right past the constant. I've got a power rule, so this becomes my new coefficient, and that reduces by 1. So putting that all together, we get that this is equal to 6u du. Don't forget our differential, because the power rule says that, yes, the exponent comes down, becomes a coefficient. That reduces by 1, but we still have to hold on to the du. And this is definitely one of those places that if you lose that du, you'll get very confused later on in trying to solve the problem. All right, so dy is equal to 6u du plus 24 v squared dv. Okay, so that's the differential of y with respect to u. So what is dy dx? Well, we just divide by dx. So dy dx is equal to 6u du plus 24 v squared dv, all divided by dx. Or a more natural way to write this would be break this up into 2, and we get 6u du dx plus 24 v squared dv dx. So even though we don't know what u and v are, we know that if we take the derivative with respect to x, it'll be 6 times the function u times whatever the derivative of u is with respect to x, plus 24v squared times whatever the derivative of v is with respect to x. So let's do another one where we don't know what u and v are implicit or explicitly, but we can still run through the derivative. So y is equal to, say, 1 over u times v. Now we can use the quotient rule, but I'd much rather in this case, especially because my numerator is a 1, think of this as uv to the negative 1. And then I don't have to use the quotient rule. I can use my power rule when I compute the differential. So dy is equal to the differential of uv to the negative 1. And this is the power rule, so my exponent comes down and will become my coefficient, and it reduces by 1. So power rule says that this is going to be negative uv to the negative 2 times the differential of uv. And now I've got product rule, so this is negative uv to the negative 2 times v du plus u dv. That's my product rule. Or more naturally, I can say that the differential of y is equal to negative v du plus u dv all over uv squared. And so that's what the differential is. My question is, what's the derivative? So how do I go from differential to derivative? It's as easy as dividing by dx. Dx there, put a dx there. Now this is kind of an unnatural way to view the derivative. It's usually nice to get the du's and dv's connected to the dx. So I'm going to kind of slide this dx up. So again, this is just algebra now. You can think of this as a variable. So it can slide up, divide into that guy, slide up, divide into that guy. And so I get that this is equal to, and I'll go ahead and distribute the negative through, this is equal to negative v du dx minus u dv dx all over uv squared. So that's the differential of 1 over u times v. In this final example, we'll look at an application of the derivative. So we're going to have a function that we want to know the equation of its tangent line. So find the equation of the tangent line to the curve y equals 9x to the negative 2. And we'll look at it at the point 3, 1. So we're trying to find a line, and since you ever learned about lines, to find a line, you need a point on it, and you need the slope. Well, we know if it's the tangent line, then its slope is equal to the slope of the curve at that point. So we need to compute a derivative, because derivatives gives us slopes of curves. So let's compute the differential of y. It is the differential of 9x to the minus 2. And the differential will slide past the 9, because that's the constant rule. Then we're going to have a power rule, so this will come down, become my new coefficient there, and I'll subtract 1. So following that rule, this is equal to 9 times the quantity negative 2 x to the minus 3 dx. And I've got dx all by itself, so now quite easy, dy dx is equal to this thing divided by dx. So they cancel. So dy dx is simply negative 18 x to the minus 3. So do enough of these and you'll be able to actually do this in your head without, this is actually a pretty straightforward one. Practice makes perfect. So great, we found the derivative. We're not done yet because the problem is to find the equation of the tangent line. So we need what is the slope of the curve at this point. So when x is 3, what is the slope? So I'm going to introduce a little notation here. For Leibniz notation, I would write, if I want to evaluate it at a point, I like to use this notation x equals 3. This will be very helpful in the future, especially when we get bunches of, we'll find derivatives with multiple variables, and it'll be key to tell us, okay, which variable are we placing in. Anyways, dy dx evaluated at x equals 3 is equal to negative 8 times 3, negative 8. Sorry. Hopefully many of you saw that. Somehow I multiplied 9 and 2 and got 8 as opposed to 18. My bad. Thanks for catching that, whoever you did. Sorry you couldn't yell at me loud enough through the computer. So this is 3 to the negative 3, which is negative 3, which is negative 18 over 27, which is negative 2 over 3. So we've got a point, and now we know its slope. So writing the equation of the tangent line is easy as putting it into slope form. So this is y minus 1 is equal to negative 2/3 times x minus 3. Because the coordinate we had was 3, 1. Right? So this is our x coordinate, x minus 3. This is our y coordinate, at y minus 1. And this is now the equation of our tangent line.